Okay, there were a few questions about this problem, so let me just make a few comments. I won't do the whole thing. I'm sure you can take it from there in case you're wondering how to figure out the angle here. What's given to you is that the distance between two telephone poles is 52 meters. And when a 1 kilogram bird lands on the telephone wire midway between the poles, right? So somewhere here, the bird comes and sits, and because of that, the wire is going to sag, right? And I'm going to exaggerate it here. So the wire will sag something like this, right? It's only 1 kg bird, so it's obviously not to scale. I'll make my bird a red bird, right? So the bird is sitting here, and that's what has made the sag, right? So what they tell you is how much that sag is. So you can see that this distance here, right? This distance here is 0.180 meters. Not able to write it very well here. That's the sag that's given to you, and the whole distance is 52. So half of 52 is this distance here, so that's 26 meters here, right? So you can use this information. This is a right triangle here to get this angle theta, right? So you can say tangent theta is equal to 0.18 meters divided by half of the distance between the poles, which is 26 meters for me. And from this you can figure out the angle, right? And once you figure out the angle, the rest of the problem will be very similar to what we have been talking about. You draw a free body diagram for the bird, right? So you have the weight of the bird in the downward direction. They tell you the mass of the bird, so weight of the bird is mass times gravity. So you can figure that out in how many newtons that is. And then from the symmetry of the problem, you can see here that the tension is going to be the same on both sides of the bird. So if I call this tension T1 here, this can be T2, but T2 is going to be equal to T1 because of symmetry in the problem, right? So you can just say there is a tension T here, and there is another tension T here, and the angle that they make with the x-axis is the same. So that's the angle theta that you have here, right? So once you have the angle, I'm sure you know how to do this problem just the way we've been talking about, right? So I won't say any more about this. You break up your tensions into x and y components and then continue on and calculate the tension. Okay. This is the last problem in the WebAssign. If we met today, I would have set up a system that looks just like this. I would have probably taken a poll from the class to say, what do you think the spring scale would read, right? From my experience, I usually get one of these three answers. In fact, one of the two answers that are most common. Some people say that this spring scale would read 0, right? And some people would say that it would read twice the weight of these masses here, right? And I will set this up for you when we meet again on Thursday, hopefully. And when I do that, you'll see that the spring scale it does not read 0, it does not read twice the mass. Instead, it actually reads just the weight of one of the masses, right? So I'll try to convince you why that would be the case. So what the spring scale reads is the tension in the string that's set up by these two weights, right? So there is a certain tension, and you insert the spring scale here to read the tension. So our best bet is to draw a free body diagram for one of these masses. So for example, if I try to draw a free body diagram for this mass m here on the left, I can say that this is my mass m here, right? You have the weight of the mass mg, that's the weight of the mass w, which is equal to mass times g, right? that would be balanced by the tension T that's established in the string. So you would have a tension T pulling up on it, right? And since the system is balanced, there is no acceleration for the system. The tension T should just equal the weight of the object, you see. And I could have drawn a free body diagram for this mass, and I would have got exact same thing. Just like this, I would have the weight being balanced by the tension T. So those of you who may have thought that the spring scale would read 0, you probably are thinking about the net force acting on the spring scale, because if I try to draw a free body diagram for the spring scale, then I would have a tension T pulling to the right and another tension T pulling to the left, and that would correctly tell me that the acceleration of the spring scale is 0, right? But that's not the reading of the spring scale. The reading of the spring scale is the actual tension in the string. Okay, so the answer for this one would be, so you can say that the net force is 0 in the y direction. So just like we've been doing, the tension is equal to the weight, and the weight is mass times gravity, and that's 48 newtons, which is the weight of one of the masses, not two. Right? Other ones here, you can convince yourselves. When you look at this one, it should be no problem to see that the tension here is balanced by the weight, right? And that's what is read by the spring scale. So another way to understand part A by intuition is that if I try to block out this side here, the spring scale doesn't know what's keeping it at rest, whether it is a wall like it is here, or it's another mass like it is in part A. You see, so the spring scale, as far as the spring scale is concerned, the tension's exactly the same as it's here, right? And I'm sure you can see here, you draw a free body diagram for the pulley, right? You would be able to see that the pulley, the tension T up here, which is what is being read by the spring scale, that's being balanced by the two tensions in the string here. But each tension is equal to the weight that's hanging here, so that's mg and then mg. So I'm sure you have no trouble seeing that the spring scale should read twice the weight here. Okay, so that leaves us to this very last part here, where a mass is on an incline, and I'm sure it's intuitive that the spring scale will read a tension that would be less than what it would read here, right? It was 48 newtons here. You would expect it to be a lot less than 48 newtons, right? And how much less, of course, depends on the angle theta of the incline. Right? And the inclines come so often in what we do, so I just want to say a little bit about how you can draw the free body diagram and how you can take the components for a mass on an incline. Okay. In part D of that, this is the situation that we have. The object of mass m is being kept in place by the tension in the string here, and of course there is the weight that the earth is acting on it, and there is a normal force from the incline on the block. You see, so if I try to draw a free body diagram for this block, and I'm going to try to draw it on an incline. So I'll draw the inclined plane again so that I can keep track of the mass. So this is the theta, and just so we can see the angles well, I'll draw the mass as a small little thing here. That's the mass, and my forces on it, right? You have the weight W, and the tension T is pulling up on it this way. That's the tension T, and the normal force is acting on it perpendicular to the surface, so that's in this direction, right? That's the normal force. So as a result, I guess you can't really see the T there. I'll draw it again here. So the block is at rest as a result of these three forces, right? So since the forces are at angles, we need to break them up into components. Now with most of the inclined plane problems, in this case this is equilibrium, it's not moving, but even we'll be looking at problems where the movement would be either up or down the incline here. So it makes a lot more sense to take the x and y axes to be, one parallel to the x-axis and perpendicular, parallel to the incline to be the x-axis and y-axis to be along the perpendicular here, right? So the reason we do this is so we can keep the x and y, well, the tension in the normal to be along, tension's already along the x-axis, so I don't need to break this up into components, and the normal force is already along the y-axis, so I don't need to break that up into components. So I just have to break up this w into a component down the incline and a component perpendicular, right? And when you take components, what do? You drop a perpendicular from the tip of the vector onto the axis. So if I do that, I have this is the x-axis here, and I drop a perpendicular here. This is my x component, right? And this is my y component here, okay? And you can see here in this right triangle, if this is theta, this angle is theta here, right? So W is the weight, that's the hypotenuse here. So if that's W, this one down here is W sine theta, right? That's W sine theta, because that is the opposite side of this angle theta, and this is the adjacent side of this angle theta, right? So writing it over here, I have a W sine theta here, and this is W cosine theta. A lot of times students ask me, why is it that sine theta is the x component and cosine theta is the y component? I just want to say that one of the reasons it's in terms of the theta is with any inclined plane problem, the ramp angle is usually what's given to us, right? And the ramp angle happens to be the angle that W makes with the y-axis, right? So this angle theta that W makes with the y-axis rather than the angle that it makes with the x-axis, right? So that's why you have the cosine for y and sine for x. Right? So once you have this free body diagram, it's easy to see that the normal force must balance W cosine theta, and the tension should balance W sine theta. Right? So in order to finish up this problem here, you can say a net force in the y direction, well, net force in the x direction should be mass times acceleration, but acceleration is 0. So I can write this down as t minus W sine theta equals 0, or t is equal to W sine theta, right? And W is m times g, and then sine of the angle that's given to you. I forget exactly what was the angle that was given on the first page here. The angle to be 27. So all that in here, I have mg sine 27 degrees, and mg we had already calculated, that was 48 newtons. So 48 times sine 27, and if I didn't do this beforehand, so it's 48 times sine 27, which comes out to be 21.8 newtons, right? So this is 21.8 newtons. So the spring scale reads a much smaller value because it's on an incline.